Now I need to model the composite beam. At first I need to come here in material property and I need to define a concrete with zero weight. So this is a copy of 32 MPa concrete, so I will put concrete 32 MPa 0, and all I need to do is just put this 0 and press OK. Why I am doing this? Because I want to add the concrete flange as a part of composite section, but actually I already have the slab here. So if I do this, I literally adding to the weight of the structure and load of the beam. That's why I'm using zero concrete, to use the stiffness of the concrete as a flange, but do not use the weight of the concrete on top of the flange in addition to the slab modeled here. Now I need to come to define section, add new property, other, general section. The secondary beam we have here is 180 UB16, so I mention here 180 UB16 composite, and I choose grade 300 for steel. No check design because the composite section cannot be designed by SAP. ETABS has this capability but SAP not, so I'm going to section designer and then I'm choosing a nice section here, put it to the center, right click, change this one to 180 UB16, and I can see the height is 173 millimeter. I press OK, and let's change this one to millimeter, which is easier to play with for section. So I'm zoom in a little bit and I'm coming here, choose this element and change this one to 32 MPa 0, and I need to calculate this. So 173 divided by 2 plus 80 millimeter, which is half of the slab thickness, is 166.5. so X center is 0 and Y is 166.5 millimeter. Height is 160 millimeter. For width of the slab, you need to see your regulation based on the space between the beams and the thickness of the slabs, and also if the beam is edge beam or middle beam, you may have different widths of concrete. But here I just assume roughly the space between beams are 1 meter to 1.2 meter. I assume 1 meter. As I said before in our webinar, because the concrete and the steel don't have the same module of elasticity, we need to convert concrete size based on the module of elasticity ratio. So roughly the module of elasticity of concrete to steel is about 1 to 10. Is not necessarily correct here. You can accurately calculate, could be 1 to 8, but let's assume 1 to 10 at the moment. So I need to reduce the length of the slab to 10% of the actual length. So I'm coming here, I'm just using 100 millimeter, and I press OK and OK, and you can see this is my composite section, converting the concrete to a steel module of elasticity. So the I value now is correct. I press down, so I have this section now, 180 UB16 composite. So I'm just choosing one span here intentionally and leave the span next to that as it is, so you can compare the result, see what's coming up. So I select all of them and I change them to 180 UV composite. but this one is 180 UV. Now let's run. Just remember, still the slab stiffness is 0.35. I just want to show you this interaction before doing another trial and change the slab stiffness to lower side. Let's see what's coming up. Okay, the analysis is finished. Now we can check the difference in results. So we're coming here using Composite G2 moment 33. Yes, you can see the moments are different now. So here we have about 17, 18 kilonewton meter moment, 12 kilonewton meter moment, but here still 5 kilonewton. What about the deflection? So if I right click here, I see the deflection decreased to 5.5 millimeter from almost 7.5 millimeter. You see, when you increase the stiffness, still the slab is participating and we end up with a smaller deflection. So this displacement could not be correct because you have the stiffness of a slab in your model and you have a stiffness of a slab here. How we can make it correct and really ensure that what is the actual displacement of this element and what's the actual load will be transferred to this, we need to minimize the stiffness of the slab above and just allow it to transfer, superimpose dead load and live load and self-weight here. Otherwise, you just trust the interaction of the finite element model and you don't model the composite beam. You just see I have a beam and I have a slab, so this is the result. So that was 7.3 millimeter before, but we were sure that the moment was not correct. So to see if the deflection was realistic or not, we can unlock the model again and change the slab stiffness for 160 slab to a small number. We tried 001 last time, if you remember. Just want to keep it here to get the same result to see if we end up with 70 kilonewton meter or not. Maybe 005 would be a bit more realistic. It's really a trial and error to see the value you're expecting to be transferred to the beam is there or not. There is no specific formula for that. You guys just need to do your own practice and find your own way, and I'm happy if you share your ideas here in the forum and we can discuss about that to find a reasonable factor for this. But mainly trial and error is a good way. It depends on the strength of the concrete, that could be different, but your hand calculation shows exactly what needs to be transferred, ignoring the stiffness of the slab. So if you want to be conservative in design of your beam, that's how you can transfer the loads. But in terms of design the slab, this model will not help you, and you need to have a separate model like a continuous beam and see what's the maximum moment of the slab, and based on that design your slab. So let's have a look at the result here using the same. You see the loads changing. So here we have about 46 kilonewton meter. Here we have 53 and 63 kilonewton meter. So those are increasing now. You see the loads are more here than here. Now let's check the displacement. So if I come here, the displacement Newton and millimeter, the displacement is about 25 millimeter. That means the slab took a massive part of float and add it to the stiffness. So you see this is a composite beam, and the composite beam is deflecting 25 millimeter if you remove the stiffness of the slab. Let's see what's happening to the others. The moment is almost 65 kilonewton meter and the displacement 25 millimeter. Here just need to probably zoom in a little bit. Okay, so for this element we have a very big displacement, 80 millimeter. You see the effect of adding that part of a slab as a flange. So 80 millimeter here and 47 kilonewton meter. Less moment but more deflection. So you clearly see the effect of participating of the slab as a shell in your deflection and interaction between other elements. So what is the result? The result is when we want to design a composite beam, we need to model that part of a slab as a flange on top of the beam, and that can be used for deflection and we can get the right moment, and the slab stiffness should be very small amount. So this is the realistic numbers we have for displacement and for also getting the moment. So let's just design these few elements and see what's coming up. So these moments are not correct, but because we have different elements, see if we design them what will happen. If I come and go to PMM ratio, these elements are not taken as a steel member, so they cannot be designed. Doesn't matter if you check them as a grade of steel, but because this is a combination of steel and concrete, it cannot be designed as a steel section. If you have a section designer but just of steel, it can be designed. But when you have a combination of concrete and steel, it cannot be designed. So you need to design it manually. The other option is leave it to the software when you design the beam, but you need to have the right moments. Let's design few more here. I believe the stress ratio would be very high. There are two reasons for that. First of all, we change the stiffness of the slab, so the slab transferring more load to the beam, so the moment is more than before. And second one, the effect of lateral stiffness of the slab hasn't been considered in the design of the beams. So if I come here and show you the stress ratio, you see the stress ratio is very high. But even if you choose them and decrease the lateral stiffness here, and this time I intentionally just changed the lateral bracing length ratio to show you the other factors like unbrace length ratio for buckling are not effective in increasing the bending capacity. So the question is, what is the proper reduction factor when we have a slab continuously connected to the beam? The answer is close to 0, because the compressive flange, which is the top flange of the beam in single span beam, is the key part of the beam to determine the bending capacity. So if I choose this factor and press OK, and again select them and design them, you see they are still red, and the ratio here is still more than 1. Why is more than 1? Definitely the moment is more than the moment capacity. So if you come here and go down, you see the moment is 47 kilonewton meter, but the bending moment capacity is 41 kilonewton meter. You also can see the bending moment capacity considering the effective length equals to the maximum moment capacity of the section. Here we call it section moment capacity, and that is because of choosing such a small unbraced length for lateral stiffness, which is correct, and this result shows the beam is over stress. But anyway, this is not correct. As I told you, still the moment here is not realistic. Here the moment is correct, the deflection is correct, but here neither moment nor deflections are correct. So long story short, if you have a composite beam, you need to model the beam with the portion of a slab acting like a top flange and reduce the slab stiffness to a very small amount. At least you can get the reasonable and correct moment and deflection, but you need to design the beam manually yourself. The beams here, yes, if the moments are correct, you may be conservative and design the beam by considering the effect of a slab, but the correct way is using this composite section and design the composite beam, because the result would be different. So this is not very economic. Using the composite section is the right way. Okay guys, this is the last part of this video, and I hope I could add some value to you and show you a little bit how to use a software in general for structural modeling, and how to anticipate the behavior of the structure, and how to tweak your model to meet your expectations.